Well, I know what's gonna happen after I do this. You guys are gonna think of me as the YouTube channel that just does all your work for you. Never mind student thinking and student effort, dang it. But fine, here are, by popular request, some moments of inertia of things. This is the first in several video series where I'll just be calculating moments of inertia like you should be doing instead of me. But the very simplest, I think, is where you have an axis and you have a line of mass. There, that's a line of mass. And so it doesn't have any thickness, thank goodness. Here's our axis. So let's get to integrating this sucker. We know that the moment of inertia is defined as the integral of r squared times dm. That's the differential mass. And if we have just a single mass at a single point, then the integral reduces to just like, hey, r squared times the total mass, right? So in this case, though, we have a slight subtlety. Let's declare that it is a length L long, this pipe or stick or something, and this is going to be the y-axis, that direction. Okay, so linear density. Linear density is this idea that linear density is just the total mass divided by the unit length. So in this case, dm, as we take an additional slice, any slice of this length right here will be the linear density times how much of a slice we've taken. So our differential slice is going to be, well, it's massively blown up right here, but that differential slice has a length dy, right? So in that case, our dm, our differential mass, is just lambda times dy. Is that reasonable? And I like using y's and lambdas at the same time. I think that's really fun. You'll see that it results in some really neat relationships. Okay, so here I am, and of course the y-axis also defines how far we are away, so it's kind of be like r, right? I guess I could write that. r equals y. Good, and then let's calculate a moment of inertia. We're taking the integral from 0 to L. That's not a variable, it's the actual given length of the stick. And then we're integrating, well, it's supposed to be r squared, but r is y, so I'm just going to call it, look at that. I'm going to call it y squared, right? And then I'm supposed to put in a lambda right here because that's what dm is going to be. It's going to be lambda times dy. Oh gosh, this is really easy. If we assume a constant density, that's what we'll do explicitly here, a constant linear density, then we can pull out the lambda. And we get from 0 to L the integral of y squared dy. Golly, even I know that integral. So we're going to have lambda times y cubed over 3 evaluated at both 0 and L. Try evaluating that at 0 with a friend. Yay! Lambda times L cubed over 3. Now, that looks weird, right? That's not what's in my book. Hey, quit it. No. Don't panic, because we're going to look each time at what the total mass is. But total mass, I use a capital M to represent total mass. Total mass is lambda times L. So in that case, wait a second, we're going to be essentially, if we're factoring out an M, we'll be dividing this by lambda L. So that's going to be, oh gosh, we'll just have m times L square over 3. That's weird, and I guess it's customary to present it as 1/3 mL square. And that's the result that's in your textbook, and that 1/3 right there is telling you that it's actually, whoa. If we'd assumed that all the mass was right here at the center and used L over 2 and just plugged it into the r squared dm equation, we would have gotten a 1/4 in front right here. So it's more moment of inertia than if all the mass were concentrated at the middle, and that's because there's an extra weighting of the stuff that's at the outside. This is not evenly contributing as that is. They are very differently contributing because of that r square. So I don't know a way to do this without an integral, and there you have it with an integral. But one other thing, as we're going through these, I'm going to present this as I equals beta times m times some distance, which is usually the length or radius of the thing, square. And then this form is super common in all the representations except for the very interesting geometries. And so all we need to do here is find this beta, and we're looking for all the integrals to simplify down to this relationship and some fraction, which in typical cases where you don't have any mass outside of this dimension right here is going to be between 0 and 1. Where the mass is concentrated locally, it would be low, and when it's distributed out, it's going to be up to a value of 1. In this case, beta is 1/3. Great, so let's do another problem. Oh, should I label this? Let's see. I for long, skinny stick. Okie dokie.